Ever wonder how robots learn to handle 3D objects, like picking up a mug without knocking over a stack of plates, with such precision? It's a massive challenge because robots don't see the world the way we do. They rely on data, and traditional methods often struggle with 3D environments. But a groundbreaking system called BridgeVLA is changing the game. Let's break down how it works, and why it's a big deal for the future of robotics. Here's the core problem. Most robot learning systems use 2D images, like the photos your phone takes. But real-world objects exist in 3D space. Think of it like trying to navigate a room using only a flat map. You're missing critical depth and spatial clues. Current methods either ignore 3D data entirely or mishandle it, leading to inefficient learning. For example, a robot might need hundreds of tries to master a task, which isn't practical. That's where BridgeVLA steps in. It's a system that bridges the gap between 2D vision language models, which AI uses to understand images and text, and 3D robotic actions. The key idea: aligning 3D inputs with 2D outputs to make learning faster and more efficient. Here's how it works. Imagine you're giving a robot instructions like, put the red ring on the maroon spoke. Instead of feeding it raw 3D data, BridgeVLA first projects that 3D scene into multiple 2D images, like taking photos from different angles. These 2D images are then processed by a pre-trained AI model that understands language and vision. But here's the twist. Instead of predicting actions in 3D space, the system uses heat maps, 2D grids that highlight where the robot's arm should move. It's like drawing a road map on a flat map to navigate a 3D world. This approach solves two big issues. First, it ensures the robot's vision. The 2D images matches the AI's training data, which was originally designed for 2D inputs. Second, by using heat maps, it leverages the inherent 3D structure of objects without getting bogged down by complex 3D computations. The result? The robot learns faster, with fewer examples. The numbers speak for themselves. In simulations, BridgeVLA boosted success rates by up to 10%, like going from 81% to 88% on a task called RLBench. In real-world tests, it outperformed existing systems by 32%, and even handled tricky scenarios like sudden lighting changes or unfamiliar instructions. But the real wow factor? It achieved a 96.8% success rate on 10+ tasks, using just 3 training examples per task. That's like teaching a robot to juggle in under an hour. Training a robot to do complex tasks is like teaching a child to ride a bike. You don't start with a mountain trail, you build up slowly. BridgeVLA does something similar. Instead of overwhelming the robot with every tiny movement, it focuses on key moments, like when the robot stops, grabs an object, or finishes a task. These snapshots help the robot learn the most important parts of a movement, just like how we remember the highlights of a story, not every detail. Now let's talk numbers. Training this system is no small feat. For example, one setup used 48 superfast NVIDIA H100 GPUs, like giving a robot a 20-hour marathon of practice. But they also tested smaller setups, like 8 A100 GPUs, training for just 1.5 hours to mimic real-world conditions. It's all about finding the sweet spot between power and efficiency. To test BridgeVLA's smarts, researchers used 3 big challenges. 1. RLBench 18 complex tasks, like pouring water or assembling parts. 2. COLOSSEUM 12 surprise scenarios like changing lights or camera angles to see if the robot adapts. 3. GemBench 92 variations of basic actions like pushing or stacking to test flexibility. And here's the kicker, BridgeVLA didn't need fancy tricks. It just used those keyframes from real robot movements. No shortcuts, just smart learning. The results? Impressive. On COLOSSEUM, BridgeVLA outperformed other models, especially when faced with wild changes. On GemBench, it nailed tasks even with brand new objects or actions. But the real test? Putting it in real-world scenarios, like adding random objects or turning off the lights. Even then, it stayed calm and focused. So why does this matter? BridgeVLA isn't just a technical win. It's a step toward robots that can adapt to real-world chaos. Whether it's assembling furniture, sorting recycling, or aiding in disaster response, this kind of efficiency could make robotics more accessible and transformative. Imagine a future where robots learn new skills as easily as we do, just by watching, listening, and practicing. That future is getting closer, thanks to breakthroughs like BridgeVLA. So next time you see a robot doing something tricky, remember, it's not just following instructions. It's learning, adapting, and getting better, thanks to experiments like this. Stay curious, and we'll see you in the next video.